What's going on? Well, it's all to do with the jet stream, as is often the case. The jet stream at the moment, well...
Talking about the jet stream and its position has become more commonplace in weather broadcasts. It is often blamed for why we get the weather we do. But why are we so interested in it? And how does it influence our weather? A jet stream is another name for fast-flowing currents of air which encircle the globe at high altitudes. The major jet streams are the polar front and subtropical jets. They can reach speeds over 200 miles per hour, but this speed is not constant throughout the length of the jet stream. Embedded within the wave-like pattern of the jet stream are localized areas of even faster winds. Even though these areas are relatively small-scale features within the larger jet stream, they are important as they provide a focus for modifications to surface pressure patterns. Their position within the trough ridge pattern of the larger jet stream influences the resultant shape and can affect the development of weather at the surface. A stronger jet on the left or rearward side of a trough will cause that feature to sharpen or extend. A sharper trough can cause deeper low pressure systems at the surface, giving stormier weather. For a ridge, this same position of the stronger jet will cause the feature to amplify. An amplified ridge can block the normal west-east progression of weather systems and bring more prolonged periods of settled weather. On the other hand, a stronger jet on the right or forward side of a trough will cause that feature to relax. For a ridge, this same position of the stronger jet will cause that feature to decline. Both circumstances have less impact on the development of surface weather systems. Jet streams affect the weather by generating regions where air ascends or descends, which can lead to areas of falling and rising pressure at the surface. Certain regions of jet streams are more favourable for rising or sinking air. To explore this, let's take a journey through a simplified jet stream in the Northern Hemisphere. Two isobars, lines of constant pressure, are shown on a horizontal surface. High pressure lies in the warmer air to the south, and lower pressure lies in the colder air to the north. The isobar spacing is closer together at the centre, showing the region of the strongest pressure gradient and stronger winds. Before air moves into the stronger jet entrance, it is subject to a balance of forces, known as geostrophic balance. This is a balance between the pressure gradient force, which acts from high to low pressure, and the Coriolis force, an apparent force that is the result of the Earth's rotation. As the air enters this region, it accelerates because of the increased pressure gradient. To maintain the balance, the Coriolis force would also have to increase, but its response is not immediate. This means that whilst the overall movement of the air through the jet stream is still eastward, there is now a component towards the north. This northwards component is the ageostrophic wind, which results from the imbalanced forces. In the entrance region of the stronger jet, this component causes a transfer of air from the right side of the jet entrance to the left side. This removal of air from the right entrance creates an area of upper level divergence, whilst air piling up in the left entrance region of the jet creates an area of upper level convergence. These areas of divergence and convergence have a significant influence on surface pressure and the weather we experience. Diverging air at high levels means that the air in the column is being depleted. To fill this depletion, air from below rises. If this region of diverging winds is stronger than the corresponding converging surface winds, there is an overall loss of air from the vertical column. As pressure is the weight of air in a vertical column, if the amount of air decreases, the surface pressure must fall. This would cause an underlying surface low pressure system to deepen, bringing increasing wind speeds and heavier rain. For an underlying area of high pressure, this situation would cause surface pressure to lower, lessening its blocking effect and allowing the eastward progression of weather systems. For the left entrance region, where air is piling up, there is an overall increase in the mass of air in the vertical column, and so surface pressure must rise. This would cause an underlying surface low pressure system to fill and weaken, bringing decreasing wind speeds and less unsettled weather. Pressure in an underlying area of surface high pressure would get even higher, continuing the settled conditions, but also increasing the risk of visibility problems caused by haze, mist, or fog. Our journey now takes us to the core of the stronger winds, where the Coriolis force has caught up with the increased pressure gradient, and geostrophic balance is restored. However, this balance is short-lived as air starts to decelerate in the widening pressure gradient in the exit region. Again, the Coriolis force is slow to respond, creating an imbalance. But this time the Coriolis force is larger than the pressure gradient force. This now creates a southward component of a geostrophic wind. This southwards component now causes a transfer of air from the left side of the jet exit to the right side. So air is now piling up in the right exit region, creating an area of upper level convergence, sinking air, and surface pressure increases. And air is leaving the left exit region, creating an area of upper level divergence, rising air, and surface pressure falls. When focusing on the regions of jet streams that are most likely to cause a larger impact in the weather that we experience, meteorologists look for the right entrance and left exit regions. When these upper-level development regions coincide with favourable surface features, such as low-level temperature or humidity gradients, we experience the three-dimensional nature and interdependencies of our complex and interesting weather.